All right. Hello, everyone. Thank you for coming to the second PhySU Colloquium now. We're kind of trying to get started with these, run them a little bit more frequently. I think in the foreseeable future, we'll have these about every Friday. So please do keep coming. I would like to welcome our second speaker in the series, Aditya, who is a third-year physics specialist student, and he will tell us about the research he did, I think, this summer at McGill University. Thank you.
So, hi everyone. I am also Aditya, just like the presenter last week, and today I'm going to talk about dark matter, and particularly the dark matter candidate that I was studying this summer, which is called the Dark Photon. And I think the title of this talk fits the whatever I'm going to talk about quite well, because it's my favorite book at the moment, and you'll see why this relates to it. So that's my supervisor. That's the PhD student I was working with. Amazing people, and I am very grateful. So the plan. We will talk about dark matter in general. What is it? Why do we care? The whole spiel. Why do we think it's there? What's motivating it? What are its properties? What does it absolutely have to do to explain the observations that we make? And then what are some candidates? What sort of models have people come up with? What are the paradigms to proposing a dark matter model and getting predictions out of it, eventually getting to experiments so that you can actually observe it. Then, in particular, we will talk about dark photons, my favorite model of dark matter. I am biased. There will be an introduction, and I will talk a bit about my research, what my summer was like, and what I was specifically working on. So, without much further ado, let's get into it. Out of all the energy density in the universe, 70% is dark energy. That's not what this talk is about. But out of all the matter in the universe, dark matter is 80%. So baryonic matter, all the normal matter that you and I are made of, falls very short of the proportion that this constitutes. It definitely interacts gravitationally. I will talk about why we think it's there, the evidence, and it has to be gravitationally interactive, and maybe it does more. Then it is a key part of the standard model of cosmology, which is called lambda CDM, and the CDM here stands for cold dark matter. Why cold? We will get to in a bit, but again, an integral part of cosmology as well. And it is also it is motivated because it can also solve some beyond standard model problems. Now, that's a big word, phenomenology. What it essentially means is that the work that we're doing in theory is in real close contact with experiment. We want to explain observational data directly. And dark matter has a multi-scale phenomenology. It has to explain observations at scale as small as dwarf galaxies, galaxy clusters, which are collections of galaxies. And if a galaxy is like a parsec in diameter, galaxy clusters can be hundreds of kiloparsecs, megaparsecs. And then eventually the whole universe, large scale structure, all the way back to cosmic microwave background, BBN, which is Big Bang nucleosynthesis, how the elements that we see today came about. So first, galaxies. That is stuff rotating around galaxies. There's stars, there's dust, there's a lot of hot matter, lots of energy, and it's all swirling around the center. If you try to measure how fast stuff moves as you move away from the center, you will find that if you go with a naive spherical model, that's the curve that you will get as you move away from the center. That's how fast stuff should move. If you just go with a disk, which is what we see, that's what normal matter for sure is, you will get that. And that is what we observe. So there's quite a bit discrepancy, and we don't know why. Then galaxy clusters. That's the image for the coma cluster. All these green contours are lines of some specific gravitational potential. And what this is showing is that this is all the mass, the baryonic matter that we do see with light. But all of these are potentials where we don't see mass, but somehow that still is interacting gravitationally. And then the more spectacular stuff, what happens when galaxy clusters collide. That is the bullet cluster. Maybe you've seen that image, but I found an amazing video to demonstrate what's happening. So these are two galaxy clusters. The blue part is dark matter. The red part is baryonic matter. When the two clusters collide, the baryonic matter interacts a lot because there's charge, there's obviously gravitational interaction, and so it sort of gets drawn back. The dark matter does not interact as much, it just passes ahead, and there's definite lag with normal matter. We say that the cross section of interaction, which is essentially how much what the strength of the interaction is, that's quite small for dark matter, and that's the image that we just saw. So, but how can we separate normal matter from dark matter? You can see normal matter with X-rays. The matter there has very high energy, and so it releases a lot of X-rays, and that's the normal matter. But then there's something called gravitational lensing, which essentially distorts everything that's behind this cluster. And when we do see the light of all the galaxies in this background, they get sheared, they get stretched, and that's because light is bending around a gravitational wedge. And the mass we get from that is much more than the mass that we can see with the X-rays. Then cosmological prose. This is matter at the larger scale. We want to explain what the structure of the universe is. And then this is a very, very important result. This is from Planck in 2015. And what this is essentially showing is the anisotropy in cosmic microwave background. The cosmic microwave background is very uniform. And that shows how much the deviations are from that uniformity. It's almost a perfect black body at 2.73 Kelvin, but there are some deviations. And what these deviations actually look like, that's very sensitive to the amount of matter that there was at this point in the universe. And when you vary this proportion even slightly, the amount of matter versus dark matter there could be changes very heavily how this works. But that's the lambda CDM model, the blue curve, and that's our observation, and that fits it really well. So with all this evidence, we think we've managed to motivate it enough that dark matter is quite the popular paradigm now, and there are other ways of explaining this stuff, modified Newtonian dynamics. We try to explain it with general relativities, but not everything works at every scale. But dark matter somehow is standing the test of that. Then, what are the properties? Darkness? Duh. But what does that actually mean? Like I said, with galaxy clusters colliding, the interaction cross-section is quite small for dark matter particles with random amount particles. And they must be very neutral to a high degree. If they were charged, they would lose energy a lot more quickly. There would be radiation. We would be able to see it. Coldness, that's the C from CDM. And that just means it has to be non-relativistic. It has to clump at just the right rates so that you can get structure. Galaxies can form, galaxy clusters can form, you get the right gravitational potentials, and stuff's not just flying around in a whole big hot ball of plasma. And it also explained that perturbation in the CM, those anisotropies. It has to be non-baryonic, not normal matter. And what that means is that it has to produce the correct density of the usual elements we see. Hydrogen is the most abundant element in the universe. The correct relic density that was produced in the early universe and has survived till now, we should get the correct number for helium, for lithium, all those elements. And that's limited by the density of dark matter. Lifetimes. If it does decay, like some particles decay into other particles, it must be slower so that it still has to survive for us to be able to see its effects. And there are also dark matter, decaying dark matter particles, candidates, where you have these two levels, an excited and a ground state, one decays into the other, but you can still constrain how much their lifetime is. And then again, self-interaction, how much should dark matter interact with itself? And you can put energy constraints, and galaxy cluster collisions are a good source of this constraint, and it really bounds how strongly it can interact with each other. And it's quite small. So that's a lot of constraints. I'm imposing a lot of rules on what dark matter could be. Surely we should know what it exactly is. It has to be a particle or some old black hole, right? Just to hammer this point home, not even close. Because that is the whole range of candidates that people have considered since dark matter was a thing. And it goes from 10 to the minus 21 electron volts, which is the smallest particles, to 1 solar mass, as big as the sun. These can be primordial black holes. The group I was working in, I was working in this area, so ultralight, so light dark matter, that's a dark photon, and the other undergrad was working on a model where dark matter could be primordial black holes. So still quite up in the air. So two important things here. The trend in this field is that because we know so little, I mean, I should say we've made a lot of effort. People have come up with really smart solutions for stuff, but we still know very little. And the parameter space is essentially when you have a theory, you have parameters in what's the mass of the particle, how strongly does it interact with other stuff. And because we don't know those numbers, we can make educated guesses. Okay, what if I said this quantity to be this? If it's this big, then the predictions I get are these. And you can backtrack to what numbers actually satisfy the physical observations that you make. And so you might see a plot like this. That's very, there's a lot going on here. And this is essentially showing that if my dark matter mass was this, and if this is how strongly it interacted, I'll get into what kinetic mixing is. But this sort of experimental, this experiment should be able to detect it. And maybe I can see if I can actually find a dark matter particle actually detected at. And you're trying to move down here. You're trying to move to smaller masses, smaller interaction strengths, and you can make predictions. And eventually, maybe at some point, one of these experiments will actually yield an event that's a dark matter detector. And the second thing is, how do we detect dark matter in an experiment? You can hope that maybe some dark matter particle comes, interacts with a standard model particle, could be an electron, could be an argon nucleus, and it scatters. This gets some extra energy, and you can detect that energy in your detector. People have there's this big experiment called xenon, which uses a big liquid xenon tank, and if dark matter comes, excites the xenon nucleus, there's more energy, it goes to the ground state, releases photons, and which you can detect. That's one way. That's called direct detection because it directly interacts with standard model. Or you can have something like this. Two dark matter particles can interact with each other and produce standard model particles. That's more energy sort of coming out of nowhere. You couldn't see that, you can see that. That's another way. Or you can go to colliders and go the other way, smash standard model particles together, get out dark matter particles, and when you do see what came out, you lost some energy because you can't see it in the conventional way. And you will notice that there's a nice symmetry to it. If you rotate this diagram this way, you get that. If you rotate this diagram 180 degrees, you get the collider scenario. And this is a really neat thing. It's called crossing symmetry. That's true for a lot of Feynman diagrams. And it's essentially, if this process happens, if I rotate my diagram in some way, do a topological transformation, I should still get a process that's viable unless there's some other symmetry prohibiting it. But anyway, that was an introduction to dark matter, and we can finally get into dark photons. So just before we start, one quick thing I want to go over. How do you actually build a dark matter model? What's the thing you're working with? How does the math? And an important thing here is the Lagrangian. If you've seen Lagrangians before, I'm sure you'll be able to appreciate all the very slick things people have done to sort of develop this formalism. But if you haven't, I will take a page out of Professor Curtin's book and just say that it's a thing that encodes the laws of the universe. So if you have a scalar field, something like the Higgs boson he was talking about, then that's what it looks like. It's always a scalar function. You give it a field, it will give you a number. And a scalar field is just at every point in space and time, it gives you a number. Then that's effectively ENM. If you've seen this before, that's the electromagnetic strength tensor. And that is the electromagnetic field. That's the 4-vector potential. That would essentially be the photon. And J here is a source. It's a charge. It's a source of current. And so that tells you how photons and charge and sources would come. And that describes a vector field. And that will be important because the dark photon at the end of the day is a vector particle. It's a spin 1 particle. And this is just a similar thing. It's a vector field, but it also has mass now. This term says that the field I'm working with is also mass. And the Praga Lagrangian is effectively the simplest sort of model for the dark photon, as we will see. Very important. This is the Lagrangian, but when you actually go to quantum field theory, when you start to quantize your fields, you will see that the particle that you do get out of this field is your photon. And that's a U1 symmetry. That essentially means if I multiply a local phase factor onto my field, it shouldn't change the Lagrangian. My physics should still say the same, and the laws I use to describe these particles should still say the same. And then a really neat thing, you saw a lot of terms in those Lagrangians, but how do you actually get to the interactions? What's happening? A formidable expression, but it's basically the same thing. There's some field. This is like the scalar field. Eta and C are the scalar fields. What this is describing is how these particles interact with each other, these fields. If you see a term like that, that's eta cubed, that's 3 eta particles coming together, and that's an interaction. In a similar way, eta squared C squared would give you that. So that's an eta and an eta and a C that's interacting, and you get those two out, that's scattering. So you can just read off effectively the interactions that you put into your theory. And now we finally meet the dark photon. It's the dark sector twin of the photon, but the only difference is it definitely has mass, and it basically never interacts with anything else except the photon. And the premise is that dark photons and photons somehow interact weakly, and the way they do this is called kinetic mixing. You have a dark photon that's just freely propagating, and at some point there's always a probability that it will convert back into a photon. Just like the diagrams we saw before, where an eta and a C sort of went to an eta and a C, that's effectively another diagram that you can get out of here. So we built a whole new world. What if this particle actually existed? And that's the Lagrangian that we're working with. Those are similar expressions. That's the usual photon, the electromagnetic field. That's the new one. That's the other U1 symmetry that we've imposed, and that's describing the vector field, the dark photon. That's the strength. And B here, that's the actual dark photon. Again, it has mass, but A that doesn't have a term like that. That's the photon, but it still couples to the usual charges and sources that we have. So that is the kinetic mixing term. That effectively says that the photon's electromagnetic fields can interact with the dark photon's electromagnetic. And the epsilon over there out front, that's the mixing strength. That's how strongly this interaction happens. I mean, we expect it to be pretty small because, if it happened a lot, we would find something, we would detect it. And that's the mass of the dark photon. And this is really simple. We just have two parameters in this theory. There's no extra embellishments here. It's a relatively simple extension. Two parameters, the mass, the mixing strength. It's a light dark matter candidate, so it's actually in particles. It's not a compact object. It's not a black hole. And sorry, yeah. Oh, sorry. Yes. Yeah, so local would just mean the phase factor that you multiply with, that's not a constant out top, but that actually depends with space and time. So instead of e to the I theta, where theta is a constant, this would actually depend on your coordinates. And that's a really strong constraint. And again, it must explain all of that. It must carry a lot of weight on its shoulders. One quick thing, let's just talk about that big ball of fire in the sky for just like a little bit. The sun, it's just essentially this big hot soup of electrons and ions just whizzing around each other. They're not bound to each other. And if you put a photon into this bath, you would see that it scatters around these ions and electrons, and it starts to behave as if it had an effective mass. It sort of slows down effectively, and so the speed is not the speed of light anymore. It's something lesser, and the dispersion relation changes accordingly. Then, so the photon in vacuum, it has two transverse modes. The polarizations, there's electric and magnetic fields oscillating perpendicular to the direction it's moving. But here, because you have charge density, you have some charge density to the electrons, the ions, and you also have this photon, you can have oscillations of the charge density itself. So it sort of couples with that, and you get a longitudinal mode as well, which is like sound, which is a longitudinal wave. It's moving. The oscillations are happening in the direction of motion. And we effectively call these plasmons now. So this compound object of putting a photon in this bath of ions and electrons, that's a plasmon. And it comes with its own oscillation frequency, which we'll call omega p. And this depends on where in the sun it's produced. The temperature of the sun sort of decreases as you go from the center to the edge, and that sort of determines what omega is at every spherical shell. So what if we actually want to see this? If they're being produced in the sun, can we detect these dark photons? Perhaps indirectly, we would be happy with that. And how many would we actually see? So that's our lab. That's the sun, the solar chromosphere, and you'll see why I've specifically highlighted the chromosphere. You have this plasma that's produced in the sun. The sun's just a big ball of plasma, and these are just moving around everywhere. There's always the probability, like we talked about, of this to convert into a dark photon. Does that, moves out, and at the chromosphere, there's a really special potential. There's this special kind of electric field, and we'll get into what it looks like, that makes it convert into a photon again. And that's the photon that we hope to detect. Yes. I mean, so the Earth has an atmosphere, right? The sun also similarly has an atmosphere. There's like a bunch of different layers. The chromosphere is just one of them. I think it's pretty thin, but it's just like you can sort of demarcate. Like the density changes quite a lot from other layers, and that's how we uniquely identify them. So the recipe of doing this as a very stylistic good is you calculate something called the spectral flux. That's essentially how many dark photons are coming out of the sun, and you multiply that with this conversion probability. First, you've counted how many dark photons will be produced. That will tell you how many of them will convert into photons back at the chromosphere, and then when they come at Earth, you can detect it. A very natural question to ask is, how do you differ these photons from the photons that the sun normally produces? And the answer would be that these have a much higher energy. The other photons are being produced from natural, the normal standard model processes, and they sort of lie on the higher end of the spectrum. So you can visibly see the energy difference. And then you can do this calculation for different masses, because we don't know the mass, it's a parameter, you can tune it, and different omegas depending on where that dark photon was produced in the sun. So let's see what these quantities mean and how we can calculate. So that's the premise. Dark photons are produced in the sun from plasmons. And one special thing is that, remember that oscillation frequency I was talking about? Essentially, when you look at all distances from the center to the edge of the sun, that range is from 0 to 300 electron volts. And electron volts, definitely that's a unit of energy, but we're working in natural units. C and h bar are both equal to 1. And so frequency and mass and energy all have the same units. So effectively, we're describing how energetic the plasma or the dark photon, wherever it's produced. So the spectral flux, one quantity that's important into calculating that is the number of plasmons in the sun at any given unit volume at any point of time. And the integral is the integral over momentum space, which means that you essentially want to know what the distribution is with each different energy, what's the different momenta of all these different plasmas that are produced. That was not rendered, that's a pi. And obviously that depends on the production rate. That varies with different momenta and different energy. And so you want to integrate all of that to get all of the dark photons that could be, all of the plasmons that could be produced. Then to go from the plasmons to the dark photons, you get the phase space integral, which is you integrate over all momenta, and you also integrate over the entire volume of the sun. Here, that's the same production rate of the plasmons, but then that also gives you the probability in every different region of the sun of the plasmon converting back to a dark photon. So that's the flux that you would expect to see exiting from the sun, and that's just a normalization factor. Like with a sphere, if you see the intensity of light from the center, it would deprecate as you move further out, and that just tells you what that intensity would be per unit area on that sphere. Then that production rate is determined with something called finite temperature field theory. It's essentially quantum field theory, but in a thermal bath. And those are some messy calculations where you use, but I can describe to you what happens with them. That's essentially, you consider the scattering amplitudes of all the processes. Some plasmons hit electrons, bounce out, and all of the scattering which is happening inside the sun, that would essentially tell you how often these plasmons are being produced. And that's determined with something called the propagator, and then you have to do an entire integral, and yeah. And then the conversion probability is essentially, you want to solve the equation of motion for the dark photon-photon mixing system. You have the Lagrangian, you can get the equations of motion from that, and when you solve that, you can see how different modes evolve over time, and then you can figure out, just like you would in a quantum system, if your system consists of some. So that's the photon, that's the dark photon. If you wanted the probability of seeing a photon after a certain point, you would just take that, and that would give you the probability. So a point here is that the Lagrangian that we originally saw, that had that kinetic mixing term, which means that the electromagnetic fields of the photon were able to interact with the electromagnetic fields of the dark photon, which means that though the fields are not orthogonal, they still interact with each other. So you can perform a slight shift, and that would mean that you can eliminate the kinetic mixing term. So the kinetic part of your Lagrangian, which is just the interaction of the field strengths, that would just be purely interactions of the photon with itself or with other photons, and only the dark photon with itself. But then that gives you diagonal mass terms, by which I essentially mean that you get equations of motion like these. So you have a mass matrix where there are off diagonal entries which you need to account for. So it's a coupled system of differential equations. You solve that and you get the probability. So that's the actual formula, and that's the integral that I showed beforehand again. But here we're just taking some derivative with respect to the frequency, the energy, and that just tells you how many dark photons are being produced for each different energy, and that's the production rate. Because these are vector particles, they're bosons. That's the Bose-Einstein distribution to sort of account for degeneracy, and that's the actual probability of conversion. So in all, what the equation was saying is this is how many dark photons are being produced in the entire volume of the sun with whatever momentum energy, and then we normalize it to see what the intensity of these would be at. And that's one of the results of my research, where the red line, which ends about here, and the yellow line, which begins from here and ends about here, the sort of approximations of what this rate would be in these two different energy regions, and the green line is the actual numerical simulation that I did. And so I talked about that resonance between 1 to 300 electron volts for the frequencies, and that's precisely that part. That's when you get a much higher production than any other energy rate, because that's when effectively the plasma has exactly the same energy, exactly the right amount of energy to convert into a dark photon. And so these dark photons exit the sun, and now we want to figure out what the probability is of them be converting back to photons at the chromosphere. And the special potential I was talking about, that's what it looks like. So it's non-monotonic, which means it goes up and it goes down. And if you want to see a lot of these photons, you want this back conversion to be resonant. You want as many of them to convert to photons as possible. And the mass, which is the parameter of our theory, if you see what the value for that is, it might intersect this potential in these 2 points, for example. And here, because this is the height above the solar surface, so imagine you're moving out of the sun in this way, at these points, that probability of converting back to the photons is the highest. And you want to have as many of those as possible, but there's a caveat. You can imagine that because we don't know the mass, we're constantly varying it. What happens if we keep increasing it and it hits this point? Then there aren't 2 intersections, but at one point it would just intersect this curve at one point. And that's the novel part here, because that was especially difficult to calculate, and you sort of reach this catastrophe point where 2 sort of intersections become one. And so once you have that dark photon exiting the sun and about to reach the chromosphere, you have again these 2 fields, and that's the Schrodinger equation. But we're making an approximation here. If the electron density in the chromosphere doesn't change much, so the potential is slowly varying, you can sort of linearize your Schrodinger equation, which originally has a single time derivative and 2 spatial derivatives, but that is just a single spatial derivative as it's moving in the z direction, for example. And the Hamiltonian there, which is sort of the energy of a system, is split into 2 parts. That's the original basic Hamiltonian, that's just the kinetic part. But here you have off diagonal terms, and notice that the epsilon parameter is this is proportional to the epsilon parameter, and because that's small, this part of the Hamiltonian is usually smaller in strength as compared to the original part, and that calls for perturbation theory, where you know how to solve this simple problem. What if you change your Hamiltonian very slightly? Can you still figure out a solution to this new problem? And we have that formalism in perturbation theory, and you can use that to solve this equation for the equations of motion of the dark photon. You do that, and that's the conversion probability that you get. Now, here, this is essentially this integral, but an interesting thing is that that integral is highly oscillatory, which means that if these differ a lot, the integral, because that's exponentiated, it's going to oscillate very widely. So it might look something like this. If that's your dark photon mass, and it will oscillate further away from that, but here it's relatively stationary, it's not changing as much. And so the conventional way of calculating the value of this expression, which is impossible to do analytically, is you would make approximation. And the usual go-to approximation for this is something called the Landau-Zener approximation, where you effectively make the stationary phase approximation that the entire contribution of this integral is just this part, and then you essentially sum all of those contributions. So we had two intersections, and so you have a sum over two parts. But this thing where you have these two intersections, if you have these two intersections, then you would sum over these two peaks. This essentially represents this sum, but you'd get something like that. So you essentially just sum over these values to get an approximate value of it. But you can imagine that if we don't know the mass and we vary this, at some point these are going to coalesce, and we have these two peaks, and eventually they're going to come as close as possible, and we're going to lose information about what the value of each of them is supposed to be. So if they were this close, maybe if you vary the mass, they sort of start to overlap, and that approximation that we made earlier breaks down. And that's precisely because the A terms back here those A terms back there, they go to infinity. So it just stops making sense. There's no good way to interpret the result. And so the entire point of this is that that's the novel approximation that we're making. We're making use of this thing called catastrophe theory, and you can sort of determine what this coalescing peaks, what the result of these coalescing peaks would look like, what the value of that actual integral is. So we do that, and because mass is a parameter, we calculate the final result, the conversion probability for all these things. Now we can do that for an arbitrary value. Doesn't matter if we go closer enough to the peak, we can still calculate the value of the integral. And that's what this looks like. Just as a heuristic, you see that this is telling you what the energy of the dark photon is. If it's at a much higher energy, it's moving really quickly, and it will pass the chromosphere really quickly. So the probability of it converting back to a photon goes down because it spends less time in that potential. So why does any of this matter at all? That's because, remember the parameter space plot I showed you? We're actually trying to see if we can build an experiment that precisely zooms in, zeroes in these regions, and actually gives us an event that's a dark matter particle detection. And this is a new signal for dark matter at Earth. We have the ways that we detect dark matter with direct detection and indirect detection. They're primarily big liquid tanks where we would expect a dark matter particle to hit a nucleus, for example, excite it, and then we'd see the energy. But with this, we can build different kinds of other different experiments that sort of probe this new space of dark matter models. And so a really slick way to also sort of double down on differentiating the higher energy photons from the usual photons that the sun produces is that to look at the sun and try to detect these photons during a solar eclipse, because when you do that, you're essentially getting rid of as much background as you can. The moon would effectively cover the cross section of the sun, so you would just be left with the ring around that, which is the chromosphere, and you would only see photons from that part. So the lower your background, the better your chances are of detecting this. And for more complicated potentials, we would like to come up with a similar formalism to actually get the conversion. But yeah, thank you.